If I told you that your grandmother's secret lasagna recipe and the traffic grid of New York City were designed using the exact same mathematical equation, you would probably think I was completely out of my mind.
I mean, it sounds totally absurd.
Right. We are so conditioned to think about cooking as this inherently human art form. The pinch of this, a dash of that, just a feeling you get when the sauce smells right. It feels spontaneous, entirely driven by intuition, maybe cultural expression, and a few happy accidents along the way. But today we're doing a deep dive into a massive reality-bending data set that basically proves culinary design isn't an art form at all. It is a highly structured, inescapable mathematical language.
Yeah, it really forces a total rethink of how we view human culture. The source we are analyzing today is this landmark April 2026 paper from the Indraprastha Institute of Information Technology in Delhi. It's titled Universal Statistical Laws Governing Culinary Design. And the sheer scope of this research is, well, it's what makes the conclusions so undeniable. The researchers built a state-of-the-art AI algorithm, like a named entity recognition pipeline, and fed it over 118,000 traditional recipes.
Over 100,000 recipes, and that's from 26 different global cuisines spanning 75 countries, right?
Correctly.
And the AI just stripped away all the romantic storytelling and broke those recipes down into raw data. It identified over 19,000 unique ingredients, and I think 270 distinct cooking techniques.
Stripping away that cultural narrative is key here because when you look at the raw architecture, whether it's a traditional Mexican mole or a rustic Italian pasta or, a really complex Indian curry, they all subconsciously obey the exact same hidden statistical laws. Yeah. The variations we perceive as these massive cultural differences are actually just different expressions of universal mathematical constraints. These are literally the same equations that predict the structure of the English language, the distribution of global wealth, and even the population growth of urban cities.
Okay, let's unpack this. Because claiming that a traditional Thai green curry is governed by the same math that builds a metropolis is a massive statement.
It is.
So to make any sense of this, we have to start at the absolute foundational level. Before a dish is even cooked, a human being has to decide what to pull from the pantry. If cooking is math, there has to be a rigid pattern to our ingredient choices, right?
Right, and there is a very rigid pattern. When researchers measured how frequently specific ingredients appear across this massive global data set, the usage perfectly mapped to something called Zipf's law. In statistics, Zipf's law describes a heavy-tailed rank frequency distribution.
Hold on, let's translate heavy-tailed rank frequency distribution into plain English for everyone. Are we just saying that a tiny handful of things do all the heavy lifting and everything else is basically an afterthought?
That captures the dynamic perfectly, yeah. In the global pantry, a microscopic fraction of ingredients is used in almost every dish, while there is this massive, seemingly endless long tail of extremely rare ingredients.
The heavy hitters.
Right. Across the globe, the absolute heavy hitters are salt, onion, butter, flour, and oil. Those 5 ingredients absolutely dominate the corpus. But what elevates this from just a quirky observation to a true mathematical law is the shocking consistency of the math. When you plot ingredient frequency on a logarithmic graph, it forms a perfectly straight descending line. The mathematical exponent for this global distribution hits roughly 1.53.
I think the easiest way to visualize this is to look at human language. Salt and onions are essentially the and of cooking.
Oh, that's a great way to put it.
Right, because they're the structural grammar. You cannot build a functioning English sentence without basic conjunctions and articles, just like you can't build most savory meals without a foundational layer of salt and alliums. They provide the necessary architecture.
Absolutely.
Meanwhile, those rare spices out in the long tail, like a specific dried lime or a rare foraging mushroom or some obscure fermented paste, those are the highly specific vocabulary words you pull out only when you need to convey a very precise, nuanced flavor.
What's fascinating here is the underlying mechanism that actually forces this distribution to happen. In complex systems theory, this is known as preferential reuse, or the rich get richer dynamic.
Rich get richer.
Yeah, think about the historical mechanics of a kitchen. If a versatile ingredient, like an onion, is easily cultivated, it naturally finds its way into a few early foundational dishes. And because it is required for those dishes, every household just naturally stocks it in their pantry.
And if it's already sitting on the shelf, you're going to reach for it when you start experimenting with something new. It's a massive feedback loop.
Exactly. The rich get richer. The more an ingredient is used historically, the higher its probability of being incorporated into future recipes. That preferential sampling is what locks the math into those heavy-tailed Zipfian distributions across all 26 cuisines. It's not simply a matter of global taste buds universally craving onions. The systemic process of recipe creation inherently amplifies the most accessible components.
Wait, if the rich get richer and everyone is just aggressively reusing the same salt, onions, and oil in this endless feedback loop, shouldn't our diets be incredibly boring by now? I mean, how did this AI pipeline ever manage to find 19,000 unique ingredients if the math is so heavily rigged in favor of the staples?
Well, the math allows for expansion, but under strict limits, which brings us to the second statistical law the researchers identified, which is Heaps Law. So, Zipf's law dictates the frequency of what we use, while Heaps Law governs how our total vocabulary, our culinary diversity grows as we encounter more and more recipes. The data proves that culinary diversity grows sublinearly. Sublinearly. Meaning the growth curve doesn't just shoot up at a steady 45-degree angle forever, it starts to flatten out.
Right. If culinary growth were linear, like an exponent of 1.0, reading 100 new recipes might introduce 100 new ingredients. But the global exponent for recipe growth sits at about 0.56. So the first 10 regional recipes you analyze might throw 30 new ingredients at you, but by the time you've analyzed 10,000 recipes in that same region, reading another 10 won't introduce a single new item.
I have to push back on that a bit. If I sit down and read 1,000 highly specific, avant-garde French recipes when I just keep finding new things, it feels like high-end chefs are constantly importing some new berry from the Amazon
Yeah.
or foraging a new type of coastal moss. Do we actually hit a hard mathematical wall where invention just stops? We don't hit an impenetrable wall where new ingredients are literally impossible to find, no. But we face aggressive diminishing returns. There are physical, biological constraints at play here. Human digestion, flavor compatibility, and, geographic availability naturally filter out the vast majority of the planet's biomass. But the true breakthrough in the paper is how Heaps' law interacts with the previous concept. The researchers proved a direct, inverse mathematical relationship between Zipf's law and Heaps' law.
Wait, so the math of the staples actively dictates the speed at which we innovate.
Yes, cuisines that rely incredibly heavily on their dominant staples, meaning they have a very steep zip curve, introduce new ingredients at a much slower rate. They have a flatter Heaps curve. If your culinary tradition is deeply historically locked into using, say, tomatoes, garlic, and olive oil for almost every meal, you simply don't have the structural real estate to introduce exotic new components without clashing.
That makes total sense.
A heavy reliance on a few foundational ingredients inherently stifles the rapid expansion of the overall ingredient vocabulary.
That is wild. The deeper the groove of the staple ingredients, the harder it is for a culture to jump the track and invent something wildly different. Okay, so we've mapped the global pantry. We know the laws of how we choose ingredients and how that vocabulary grows. But a pantry is just a list of stuff. A recipe is an active instruction manual. We need to zoom in on how these ingredients are actually combined into a single pot.
Yeah, and this transition from the pantry to the individual dish introduces the Menzerath-Altmann law. In linguistics, this law dictates that the longer a word is, the shorter its syllables tend to be. In culinary design, it dictates a fundamental trade-off between the overall size of a recipe and the complexity of its individual units.
When we talk about complexity in this context, what are we actually measuring? Are we talking about how hard an ingredient is to chop or how complex the flavor is?
Good distinction. The researchers define ingredient complexity using an information theoretic measure based on rarity. If an ingredient is incredibly rare within the global corpus, say, a highly specific fermented shrimp paste, it carries a very high level of informational complexity. What the data reveals is that shorter recipes, dishes with very few components, heavily feature those rare high information ingredients. But as a recipe gets longer, as you add more and more items to the pot, the average complexity of the ingredients sharply drops.
Here's where it gets really interesting. This is the exact same logic you'd use to form a musical band. Think about a jazz trio. That is a very short recipe, just 3 musicians.
Oh, I like this.
Yeah, in a trio, every single instrument has to play a highly complex, unique part. The bassist is walking a complex melody, the drummer is playing polyrhythms, the pianist is soloing. They all carry massive informational weight. But if you try to scale that up to a 15-piece orchestra, a long recipe, you can't have 15 people playing wild improvised solos simultaneously. It would just be chaotic noise. In a long recipe, you need a majority of basic, Simple instruments just holding the rhythm and playing sustained notes so the whole structure doesn't collapse.
The jazz band versus the orchestra captures the dynamic perfectly, and the reason you cannot have an orchestra of 15 wild soloists comes down to a biological bottleneck. This raises an important question. Why do we see this specific trade-off across every human culture? Without exception, it is a reflection of human cognitive and sensory limits. We physically, mentally, and biologically can only juggle so many complex flavors and procedural steps at one time.
Right. If you throw 15 incredibly rare, overpowering pungent spices into one dish, your palate just blows out. You can't distinguish anything anymore.
Exactly. The palate gets overwhelmed and the cook gets overwhelmed too. The researchers noted that across the globe, the average recipe requires about 9 procedural steps. If you are trying to balance 15 highly sensitive, complex ingredients, the cognitive load of managing the timing, the heat, and the interactions becomes impossible.
It's just too much to track.
Yeah. The Menzerath-Altmann law in cooking reveals a universal human constraint, the trade-off between expressivity and efficiency. We desperately want our food to be expressive, but we also need the process of cooking it to be efficient and stable. When a recipe grows large, the mathematical curve hits a minimum around 13 ingredients, where we naturally default to simple, reliable, common staples to keep the entire system from failing.
It's subconscious culinary load balancing. We are running advanced resource management in our heads while we stand at the stove. So we've decoded the pantry, and we've decoded the recipe structure. Let's look at the physical output. I want to transition from the process of cooking to the actual nutritional reality of the food we're putting into our bodies. Because up to this point, we've just been talking about flavor and procedure.
The nutritional analysis is arguably the most surprising finding in the entire study. The researchers extracted the macronutrients from these tens of thousands of dishes, specifically the carbohydrates, fats, and proteins. Given the wild diversity of ingredients and cooker styles, you might logically assume that the nutritional content would fluctuate randomly across different cultures. But the data shows that the macronutrients across all global cuisines form a highly specific log-normal distribution.
Wait, if you're looking at natural variations in the world, why isn't this just a standard normal distribution, like a classic bell curve? I mean, human height, weight, standardized test scores, they all naturally fall into a bell curve where everything averages out in the middle. Why does the physical output of our food obey a completely different mathematical shape?
If we connect this to the bigger picture, it comes down to a fundamental difference in mathematics, the difference between addition and multiplication. A standard normal bell curve occurs when you take independent variables and simply add them together. If you took random raw ingredients and just piled them onto a plate without them ever touching or interacting, you might get a normal distribution of nutrients. But a log normal distribution occurs when processes multiply or compound on top of each other.
Compounding, like interest snowballing in a bank account.
Exactly that. Think about the physics of cooking a meal. You aren't just doing simple addition, you are inducing compounding chemical transformations. You slice a piece of garlic, which mechanically releases enzymes. You introduce that garlic to hot oil, changing the oil's viscosity and infusing it. The heat triggers a Maillard reaction, which fundamentally alters the amino acids and creates hundreds of entirely new flavor compounds. Then you deglaze the pan with wine, which alters the pH of the entire mixture, changing how the proteins behave.
So cooking is a multiplicative aggregation. The physical output of step 3 is being multiplied by the chemical reaction of step 4.
Right. And because these chemical and physical processes compound multiplicatively, the resulting macronutrients are forced into a log-normal distribution. They exhibit an incredibly narrow dispersion and near-perfect symmetry when you plot them in log space. The ingredients we choose are dictated by combinatorial laws, but the final digestible nutrition we extract from them is governed by log-normal laws because of the compounding physics of the cooking process itself. The fact that this holds mathematically true, whether you are baking a delicate French souffle or simmering a massive pot of Mexican mole, is simply staggering.
It is mind-blowing, but, it leads us to the biggest mystery of this entire deep dive. How did this happen? We are talking about 75 different countries with massive geographical and historical barriers. An ancient cook in rural China wasn't sending letters to a cook in ancient Rome to make sure their Heaps Law exponents aligned at exactly 0.56. If nobody was consciously trying to make this happen, how did thousands of years of human history independently arrive at the exact same math?
To solve that mystery, the researchers went beyond just analyzing the data. They actually attempted to artificially recreate it. They built minimal stochastic generative models. In simple terms, they programmed a simulation, an empty virtual kitchen, with a synthetic pantry of about 15,000 ingredients. The goal was to see if they could get an AI to evolve artificial recipes that perfectly matched the human mathematical laws using only a tiny set of rules.
Well, if they built a simulation, they had to give the AI some boundaries. I'm guessing they didn't just let it mix chocolate, beef, and garlic together randomly and call it a recipe.
No, pure randomness wouldn't replicate human culture. They programmed the simulation with just three simple evolutionary rules. First, preferential reuse. As we established earlier, if an ingredient is popular, the system is more likely to pick it again. Second, sample space reduction. This is the boundary you just mentioned. The simulation acknowledges compatibility constraints. The ingredients already in the bowl physically limit the valid options for what can be added next.
Right, if you start with soy sauce, you've immediately reduced the probability of adding Parmesan cheese. What was the third rule?
Evolutionary modification. This is the core engine of culinary history. It assumes that humans almost never invent a dish from absolute zero. Instead, you take an existing recipe and you do one of three things. You copy it exactly, you add one new component, or you substitute one component for another.
So what does this all mean? It means human cooking is essentially open source software. Nobody is sitting in a void writing a program from scratch. We take our grandmother's stew, which acts as the base code, we copy it. But maybe a drought wiped out a specific crop, so we substitute a local root vegetable. Or maybe a spice trader came through the village, so we add a pinch of something new. It's iterative, evolutionary branching.
The open source software analogy is precisely how the math functions. And when the researchers hit play on the simulation, those three simple rules, preferential reuse, sample space reduction, and evolutionary modification, perfectly recreated the Zipf, Heaps, and Menzerath Altmann laws. The synthetic AI recipes matched the human global exponents flawlessly.
That's incredible.
It is. This realization is monumental because it officially marks the birth of computational gastronomy.
Wait, computational gastronomy, that sounds like an AI just generating recipes. But can an algorithm actually understand what tastes good to a human tongue? Or is it just blindly painting by numbers based on statistical probabilities?
The brilliance of computational gastronomy is that the algorithm doesn't need physical taste buds. Because we now know that human preference, biological constraints, and cultural compatibility are entirely encoded within these mathematical laws, the AI can use those laws as a map. We can program an algorithm to systematically explore the vast, uncharted spaces of possible ingredient combinations. It can generate entirely novel, never-before-seen recipes that are guaranteed to be mathematically and culturally authentic to the human palate, simply because it obeys the generative rules of human taste.
Think about the journey we've just been on through these sources. We started at the base level of the pantry, discovering that our absolute staples, our onions and our salt, form a Zipfian grammar, an inescapable mathematical foundation of how we build flavor. We saw how Heaps Law places a strict mathematical speed limit on how fast we can introduce new things to that pantry. We explored the Menzerath-Altmann law, visualizing how our own cognitive and sensory limits force a strict trade-off between the length of a recipe and the complexity of its ingredients. And finally, we saw how the physical, compounding act of cooking itself forces the actual nutrition we consume into strict log-normal distributions.
It completely redefines the concept of a recipe. A recipe is no longer just a cultural artifact. It is a compositional symbolic system.
And the real value of understanding this isn't just to impress people with math facts at your next dinner party. It means that the future of food is fundamentally computable. If we understand the exact mathematical framework of a traditional beloved dish, we can use algorithms to precision tweak those recipes. We can alter them to optimize for human health or to integrate highly sustainable, climate-resistant ingredients without destroying the cultural soul, the flavor profile, or the mathematical harmony of the food. We can evolve our diets to survive the future without losing the deep human joy of eating.
Yeah, it provides a rigorous scientific framework for navigating food innovation without losing our cultural heritage.
But it leaves you with one final, very provocative thought to chew on. If human cooking something we have always romanticized as being deeply intuitive, uniquely messy, and profoundly creative, follows the exact same generative mathematical rules as the evolution of natural language and the economic growth of cities. Well, what does that mean for our other human endeavors? Could an AI soon predict the next major global fashion trend or map out the exact evolution of pop music for the next decade just by running these exact same generative mathematical formulas forward? It makes you wonder how much of our celebrated human creativity is truly spontaneous, and how much is just us unknowingly calculating the next step in a massive, beautiful mathematical equation. Until next time, thanks for joining us on The Deep Dive.